Okay, so last time we talked about natural transformations, right? And using string diagrams and so on. But I reminded you about these two ways of combining natural transformations, right? There is vertical composition and horizontal composition. And this is very important because composition is, as you know, category theory is all about composition. So having something that composes is extremely important. And we saw that vertical composition is sort of automatic. So we could define transformations between functors as these families of morphisms, and they would compose vertically without any conditions. But when we try to combine them horizontally, you remember there was, I drew this diagram where we are having four different functors, and like at every level they split into two, right? They fork. And then at the end we get, from a single object on one side, we get first to two objects, because we have two functors, and then we have two more functors, so they split into four objects. And there are two different ways of connecting them, right? And it turns out that these two ways of connecting them are equivalent only if there is naturality condition is satisfied. And I had this epiphany after last time that this could be considered a condition for composition, that we can like reverse the thinking and say, like, what kind of transformations between functors would compose nicely horizontally, right? Because vertically they would compose no matter what. But in order to compose them horizontally, we require the naturality condition. So natural transformations are the kind of transformations between functors that compose. And I think that's like a really important insight. That we require naturality because we want them to be composable, not the other way around. And we talked about adjunctions, right? So adjunctions, we have these two categories. And it's always hard to remember, like, which one is left, which one is right, right? I mean, there are two categories. I call this C and I call this D, right? And there are these two functors, left and right. And you start with some object here, and you get LA, right? And you start with some arbitrary object B here, and you get RB, right? And the junction is when these morphisms here are in one-to-one correspondence, and in fact naturally isomorphic. These two onsets are naturally isomorphic. So when you move A around or you move B around, this mapping moves smoothly. It's like naturality means that there is some kind of smoothness when you start moving things around, right? Now the way to remember which one is left and which one is right, and this is like a general thing that we'll also see in Khan extensions, okay? Think of left as liberal and right as conservative. That's the trick, okay? So liberal is something that will like freely create things, right? So a left adjoint is something that creates free objects. So if you have algebras, this will create free algebras. If you have monoids, this will create free monoids. they're always created by the left functor in the part of the adjunction, whereas the right functor is conservative and it wouldn't try to like get rid of structure. So this is usually when you have this forgetful and free adjunction. Right is the forgetful one always, and left is the free one. So this is the conservative one. It does not add anything. It just tries to keep things as simple as possible. It gets rid of the structure. This one just generates really abundant stuff. You know, it's like a free monoid will just generate all possible multiplications that you can think of, as long as they follow the rules. Right, so this is an important thing to remember because we'll be talking about free and forgetful functors a little bit later when we talk about monads. And then I said that there is a different way of defining an adjunction. So this is one way, it's like say natural isomorphism between Helm sets. The other way is to define these two natural transformations called unit and co-unit. So it's completely equivalent. Instead of saying that, you can say, well, do we have a unit and co-unit? So a unit is a natural transformation that goes from the identity functor to the endo functor that goes first left and then right. So first left followed by right. Okay, so that's how we write. Right? Or in other ways, we go. This is the left, so this is the free functor. If we have free forgetful adjunction, this will be the free functor that generates a bunch of stuff, and this one forgets about the structure. Right? And the other natural transformation was going the other way around. So it was going to the identity functor, but it was going from L after R. Okay, so it first goes forget and then create new stuff, right? And then we have to like simplify it down to identity. Right? So we have these two natural transformations, and these two natural transformations now, since we have this new language of string diagrams, we can draw this, right? So how would we draw these diagrams? So this natural transformation starts from the identity functor. Remember, identity functor, we can draw it as a dotted line, or we can not draw it at all, right? And at the end, we are supposed to get R after L. So these are the two strings corresponding to the left and right functors, right? And then there is this natural transformation in the middle that connects them, right? So it connects the identity to this stripe. So a combination of these two functors, right? The composition of these two functors is just this stripe. So we draw it like this, okay? So this is eta. And I'm not going to draw this, so I'm just going to say eta here. So eta is a diagram that looks like a cup, okay? Now epsilon is kind of the opposite, right? So we start with LR, right? So here are these two functors. And then there is nothing on this side, this identity functor. So these two are connected with epsilon. So that's our natural transformation epsilon, right? So if you follow this, sort of scan this diagram from the bottom, you start with L after R, and then you hit this natural transformation, and it transforms L after R into identity. And that's it. And now there are these coherence conditions for this thing on top of naturality, right? How can we can take these two diagrams and combine them in two different ways, okay? And the coherence conditions, also called snake identities, come from two ways of combining these diagrams. So we can say, okay, we have with eta, we can go like this, and then we can follow it with epsilon like this, right? So we combine, so this is sort of like a diagram. Some people call it a snake, you know, or sort of like a plumbing diagram of a sink, right? And this is supposed to be equal to just a straight line. Does it work? Well, let's see, because, you know, so this will be R, right? Goes through eta and becomes L. So this line here is L, right? But then epsilon turns L into R, and we end up in R. So this is actually an identity natural transformation on R, right? Now, if we want to write it as an equation, we scan it from the bottom, right? And we get, at this level, what do we get? We get epsilon, but we also get R, right? Remember? So this is a horizontal composition of epsilon with R. And if you remember, this is notation that says if one of this natural transformation and the other is a functor, it means that we really mean a natural transformation that's an identity from R to R, identity natural transformation, okay? So this is identity natural transformation from R to R. So that's this part, and then we keep scanning it, right, until we hit the next one. So we are composing this natural transformation, but now it's vertical composition, right? We have gone vertically. So we are composing it vertically with this natural transformation, which is R composed horizontally with epsilon. And this is supposed to be identity at R. Okay? Identity natural transformation. So this is called the snake identity. And you can see that this is a combination of vertical composition, the filled dot, with horizontal composition, the empty dot, right? And if you don't remember which one is which, you know, this is the diagram that tells you. And of course, so this is one snake, and there's also the other snake, right? Which will go like this. Right? So this thing would be an epsilon, so this is L, this is R, and this is eta, and this is L again, right? So it fits. So it's like a plumbing, fitting the plumbing so that these two conduits fit together, and this is supposed to be, so it's a string diagram, so we pull the string, right, do the thingy, right, the sound effect, and we get a straight line from L to L, right? And again, we can write it, you know, scanning it from the bottom. Okay, so this is, first we go L after eta, right, and it's horizontal, now vertically composed with epsilon after L, right? And this is supposed to be equal to identity on L. And that's it. So these are the snake identities. Or when you draw them as the regular diagrams, they are actually triangles. So they are sometimes called triangular identities. So you hear somebody's talking about triangular identities. That's the same thing. Okay. So in other way, you can forget about these isomorphism, natural isomorphism between homesets, and you can say, if I want to show that two functors are adjoint, it's enough if I define these two natural transformation epsilon and eta, unit and co-unit, they are called, unit co-unit, and show that they satisfy snake identities. And that's totally equivalent. And in fact, you know, it's like if you want, you can do a homework. And starting with these natural transformation, can you recover the identity of these two homesets? You can do it cleverly. Okay. So now, the interesting thing is that every time you have an adjunction, it also defines a monad. Okay? In fact, it defines a monad and a comonad. How come? Well, first of all, every adjunction defines two endofunctor. One endofunctor is R after L, right? So if you go first L and then R, you end up in the same category. Okay, so R after L is an endofunctor on C. So it goes from C to C, right? And there's another endofunctor, which is called L after R, right? It will be an endofunctor on D. It goes from D to D. So we have these two endofunctors for free, right? And now, one of these endofunctors happens to be a monad. How do we know that it's a monad? Well, a monad has unit and multiplication, right? Now, unit, okay, now you see, like, we are really reusing the same Greek letters everywhere, and there is a good reason for this. This eta, we used it as a unit in the same letter as a unit in a monad, right? Well, it kind of has the same form, right? So, if we say that R after L, we give it a name. We say this is T. T equals R after L, okay? This combination of functors, this composition R after L. So R after L goes like this and comes back here, right? That this endofunctor T has a unit, right? Unit. Remember what a unit for a monad was? It was a transformation that went from IT to T, right? In Haskell, that was our return, or pure. It went from, it's like the component of it would go from object A to object NA. We call TM in Haskell, but it's the same thing, it's just letters, right? So that's our return. Return, or eta in mathematics, right? And it really is the same, right? So if T is RL, we have this immediately, okay? Now we need also this mu. Remember what mu was? Mu was what we in Haskell call, or you might know it as flat map, right? But it's join in Haskell, or flat map in Scala. So mu goes from T after T to T, right? t squared to t, or from join in Haskell goes from m of ma to ma, right? So we replace t with m. And this is a component of mu. Mu is a natural transformation, so it's a polymorphic function, and its component at A is this. Okay. So our T now is this composition R after L, right? So if we put R after L here, and then combine it with R after L again, can we transform it into R after L? How would we do that? Well, L after R, we have a transformation that transforms L after R into identity. So we can shrink this L after R into identity, and we get R after L. So mu can be defined as a horizontal composition of R after epsilon after L, right? When R and L here, because they are composed with a natural transformation, are understood as identity natural transformations from R to R and from L to L, right? So this is what we call whiskering. Sometimes when we combine natural transformation with a functor, it's called whiskering. Okay? So, have I shown you that we have a monad? No. Now, in order to show you that this is a monad, I have to show you the laws, right?
Yeah.
So, it looks nice on paper, but will it work in real life, right? So we have to show. But fortunately, right, we have our string diagrams. And with string diagrams, you can just do this very quickly and easily. Okay? So, string diagrams for this. So, R after L. So, our T is R after L. So, it's a stripe. Okay? It's a stripe like this. So, so before, when we had the monad laws were like this, right? So we had mu here and eta here. That was one law. The other was eta here, mu here, right? That this is equal straight line and this is equal straight line. So this is the pulling of the diagram, right? So what does this look like for our stripes? Okay. So if we replace this line with a stripe. Okay. Oh, what is? Okay, so I have to show you what epsilon is and mu is. Okay, and after a break, I'll show you how to do the diagram. So epsilon is well, epsilon is this, right? So it corresponds in monadic language. It corresponds to this T, but T is really R after L, right? So this creates the stripe from nothing, right? And mu, running out of space here. And mu will start with two T's, right? Which is R, L, R, L, and combines them into one R, L, right? So how can we do this? Well, we'll put epsilon here, right? And this is exactly what our mu is here. Mu was, where did I write it? Oh, here. So mu at this level is R after epsilon after L, right? So this is our mu. So this is eta, this is mu, and these are the stripes. And this corresponds to monadic mu. Replacing stripes with lines, we get them. Okay? So let's take a break now, and after the break I'll show you the identity.